Hello all, welcome to this tutorials in which we'll be continuing our discussion on CNNs. The main part of this tutorial is understanding how do you get a pre-trained model, and then how do you infer from a pre-trained model, and then how do you modify the pre-trained model, and then how do you extract embeddings from a model. So now, first, let's try to understand how do you load a pre-trained model. See, the idea of loading a pre-trained model is all these big networks that came for that ImageNet challenge, they came up with publishing their weights. They used to give the instance and as well as the weights of the model. Now, because of which you can use those weights, and rather than starting from a point which is random, you can use those weights and then you can just fine tune them. Okay. So now a couple of networks that came are in this. One is VGG. Okay. Now here is how the VGG networks look like. Now in VGG, what they did was they stacked a lot of convolution layers. Now let's try to understand. Now VGG had these different versions: A, LRN. Now LRN is layer normalization. B, C, D, E. Okay, these were the different versions in which A had 11 layers. Now you can count it: 1, 2, 3, 4, 5, 6, 7, 8, and then you have 9, 10, 11 layers totally. Okay, including the layers in MLP. Now this is the same. In addition to that, there was a layer normalization. Here you had 13 layers. So 2 added. Here you had 16 layers. Okay, like this. So on and so forth. 16 layers and 19 layers. So let's try to understand this, because whenever we want to understand a convolutional layers, we have to know those hyperparameters, how many filters are there, and then what is the size of, what is the spatial extent of each of the filter, what is the stride and what is the padding. See, since they haven't specified stride and padding at all in any of these network description, we can consider the stride is 1 and padding is 0. That means that there is no padding. Now that leaves us what is the kernel size, what is the spatial extent of the filter, and then how many filters were there. So you can see here con 364. That means that the size of the kernel is 3, and then there was, in this layer, there were 64 filters of them. Now this is given to a max pooling. Now whenever in max pooling also they haven't specified the kernel size and then the stride. Now therefore you have to consider it the default value, which is 2 cross 2 is the kernel size, and then the stride is 2. That is given as an input to this. Now here the input channel is 64, the output is 128. So here you have 128 channels, and then that is passed through a max pooling, and then again you have a 3 cross 3 kernel, in which you have 256 filters. Now that 256 again is given to this layer. Okay, now this is input is 256 layers, output is also 256 channels, again a max pooling, so on and so forth. So now whatever is the final output here, that is converted to a vector, and then you get 4096. You convert that vector into 4096, 4096 to 4096, 4096 to 1000. Okay, and then you pass it through a softmax to get the posterior. Okay, now similarly we can extend the idea of weights here also. Okay, now then the question is, they started from 11 and then came to 19. Why did they stop at 19? Okay, they would have went on stacking even more convolutional layers, right? Now, what was the issue? Now, this issue is similar to the idea of the vanishing gradient that we saw in RNNs, okay, in our theory discussions. Uh, because of too much of transformations, now we need the gradients become close, near to 0. Okay, so because of which the impact, the modification you cannot see in the initial layers, because of which the learning will be not good. So now how do you solve this problem? Now, if you just stack multiple convolution layers, now we used to see the vanishing gradients problem. Now, then the whole question that arises is, okay, now how do you solve this problem? It's exactly the same way in which we solved the problem of vanishing gradients in RNNs. Now we have a path in which we allow a function to learn identity. Now that means that you take a connection and untransformed input which is there, you give it to the next stages. Okay, that is what ResNet does. Okay, that is residual connections. Here you can see you get an image, you have this initial convolution layer, and then after that, for each convolution layer, you see a connection here, when which untransformed identity operations are allowed. Okay, you have this. Similarly, for each two convolution layers, you see this connections. These are known as the skip connections, because of which you are allowing the passage of the untransformed input, because of which you resolve the problem of the vanishing gradients. Okay, so now because of which here we were able to have a convolution layer with 152 layers, quite deep actually. Okay, so in our thing, we will be just looking at the first two things, ResNet 18 and ResNet 34. We will not be going with any of these. These are quite huge. Okay, so now then how is this there? Now you can see here first is you have this image which is 224 cross 224 cross 3. That is the input. You have a 7 cross 7 kernel. You have 64 filters and the stride is 2. We don't have the padding. Okay, now that is passed through a 3 cross 3 pooling with stride 2. Now this is common for all the networks. And then we see for each of those columns, now you have this repeated twice. Now that means that after these two operations, which is having 3 cross 3 kernel size and 64 filters, now stride is 1 and padding is 0. After these two, you have a connection. Now that is the reason why they have mentioned this in a square brackets. Okay, now after this, there is a skip connection, exactly similar to that. Okay, after 2, you have a skip connection. Like this is repeated twice. Now that means that you have 4 convolution layers here. Similarly, here also, you have a 4 convolution layer. Here also you have 4. Here also you have 4. Total is 16. This is 117. And then whatever is the output, that you convert it into a 1000-dimensional value using a fully connected layer. Now that is 118. 16, 17, 18. So it is known as ResNet 18. Okay, so you have 18 layers of weight. Now this is ResNet 34. Now when which this particular is repeated thrice. Now as you can see here, this color which is there, 1, 2, 3, it is repeated thrice. Similarly here, 1, 2, 3, 4. You can see that this is repeated 4 times. The next one is repeated 6 times, so then 3 times. So like this, now this is how the ResNet connections work. Okay, the idea of skip connection, now when which you are allowing the passage of the identity. Okay, so now we will not be looking at the implementation of them. We will be directly taking the instance which is already there in the PyTorch repository with the weights, and then we'll be going ahead with that. Okay, now let's do that. Now torch you need, and then you need this F which is functional. Then you have torch vision.models. Okay, now what are the models that you are getting? You are getting VGG19 and its weights, ResNet 18 and its weights, ResNet 34 and its weights. You are importing all these things. Okay, and then you are porting onto your device. Okay, you are enabling the device, and the input is 2 cross 3, 20, 224, 224, 224. Okay, now this is your number of dimension. Now this is your spatial size, 224 cross 224. Now what is this 2? This 2 is the batch size. Okay, now first always we have the batch followed by the input. Okay, I'm taking 2 examples, 2 dummy examples. I'm generating it randomly. Now see, once I pass it, now if everything is fine, it will just give me some dummy output. That's fine, no problem. Okay, but that is a straightforward indication that the forward process is happening properly. And because the forward process is happening properly, now there is enough uh, information to perform a backward pass. Okay. Now then, how do we load the pre-trained models? Now VGG weights. Now VGG weights dot default. Now we use this resnet weights dot default. We use this for loading the weights. Okay. And then from this you create instance. So you got the weights VGG 19. Okay. Weights is equal to these VGG weights, and then you put it onto the device, to device, and then you are putting in evaluation mode. Now that means that you're not doing any kind of a training. Okay. Similarly, you get the weights. If you want to do some kind of a training, don't put this eval. That's all. Okay. You're porting onto the device. So because of which now you have instances of the VGG, ResNet 18 and ResNet 34. And please remember that the input size is still 3, 224, 224. Okay, this is the ImageNet size. Okay, we are dealing with that specific size itself. Okay, and then we are looking at the forward pass VGG model. You pass this dummy X that you have created. The output will be a vector with 1000 values. This is the logits. Okay, the logits with 1000 values. Similarly, you do it for ResNet 18. Similarly, you do it for ResNet 34. I'm just extending them. And then you apply the softmax. F, that is the functional that we have used. Okay, F dot softmax of VGG logits, dimension is equal to 1. That means that you consider it as a column and then apply the softmax. Now this will give you the probabilities. Okay, this will give you the posteriors. Okay, and then you're just looking at its shape. Okay, all of them will be 1 cross 1000. You have two examples, so it will be 2 cross 1000. Okay, which makes sense. Okay, that's what you're seeing here. So now, this is how you just pass the data and obtain the things. Now, whenever we are dealing with a 1000 class problem, now there is one thing that normally people have. It is they will take top 5 thing. See, what happens is, now if you have a 10 class problem, now then on an average, now you will be having equal. If you go ahead with an equally likely assumption, now that means that each posterior, that is p of y, is equal to some I given x. Now it will be 0.1. If you have a 1000 class, it will be even far lesser. Okay. Therefore, they take top 5 values. Now I'll just show you how to do it. This is a simple way to do it. Now we are printing the top 5. Now you get the categories. Now why do you need the categories? No, because this is a 1000 class problem, and then all these categories are predefined. So we know what are those 1000 classes. Okay, it's already there. So and then now it is saying that for probability dot size of 0. Now what is the probability dot size? Now that is 2 of 0. Now that is, if you see it, it is 2 comma 1000. So 0 is this 2. So that means that you are repeating it twice. You get the top 5 probabilities and the respective index. Torch dot top k, probability of I, k is equal to 5. Now this will give you the top k. Now that is top 5 that you are going ahead. And what is the model and which sample you are looking at? It enumerates and then gives you, now what is the category, what is the probability, and then what is the class ID. Okay, that you can see it here. Whenever we did it for the VGG sample, you get it as now velvet, which is the ID with 885, and then the probability is 0.04. This is the maximum probability. This is random images, just giving. So, and then the label is walk, the ID is 909, so on and so forth. Okay, this is for sample 0. Okay, and then similarly for sample 1, now you can see. You can get the categories as well as the probabilities so that we can look at them. And please remember that these are, the probability distribution is across 1000 examples, 1000 classes. Okay, fine. So this is how you take a pre-trained model. These are the pre-trained models, obtain their weights, and then do the inference. Okay. Now, if you want to do the training, that is also fine. So you can use the same model weights, and then you can start the training. But here there is one thing, that is the number of classes is fixed. Why am I saying the number of classes is fixed? Because of the output. Now this is giving you a vector of 1000 dimension. Now that means that you are using a 1,000 class problem. That may not be true always. Okay. Now sometimes, so let's say that you want to go ahead and do something, some X-ray or MRI classification. See, in those cases, you might not have 1,000 classes, but rather than starting the training from the scratch, you can take already pre-trained models which are there and then start with that. Okay. Now, what is the use of it? See, the major use of that is already whenever it's a trained model, that means that it knows how to identify the basic shapes. Okay, it is empirically known that the early layers which are there will actually be recognizing the basic shapes like edges, corners, and stuff. Okay, on top of it, you build the thing. So since they are already trained, they know how to recognize a couple of things. Now, rather than going ahead and retraining everything, so let's start from what we know. Okay. Now this is like, now for example, you have learned how to ride a bicycle. Now, if you want to ride a bike, now you don't start afresh. No, you know how already how to balance. Yes, the weight may be different, but you already know how to balance. So you can go ahead with that. Okay, with that balancing, and then you can go ahead with that. Okay. So now let's do that. Now, how do you modify them? See, to modify them, first we should understand. So let me print this VGG 19 model. So what happened? Oh, okay. So, okay, it will give me an error because I haven't defined, because this is the runtime is gone. Let me run this. Take a moment. So it's downloading. Just give it a moment. Okay. So VGG model. What is that? VGG model. Okay. Not 19 model. It's just the So you see this feature extractor first, and then you see this classifier. Now, this classifier, you want to modify this last one, which is 4096 to 1000, which is there. Let's say that you have 5 classes. You want to modify this 4096 to 5. Okay. Now, we are still assuming that your input size is 224 cross 224 cross 3. Okay, if that is not the case, then you have to actually, if your input is of a different dimension, you have to actually sit through and compute the output so that you change this, the final feature size, input feature size, which is there. Okay, now consider that if your input size is 152.152, now then the output size of all these operations will change, because of which the input for the classifier in this change. Okay, because of which you have to compute them again. Okay, so this is the, so that means that assuming that your input is 224 cross 224 cross 3, you have to modify this 6th layer in the classifier. Similarly, if I take the ResNet in a similar manner, so this ResNet 18 model, if I can print them and see, so layer 4, now finally, so you have to modify this FC, ResNet model of FC, which is 512 to 1000, which is there. I have to modify 512 to some other size, whatever. If it is 5 classes, 5. Now the same thing with ResNet 34 also. Okay, they follow the similar structure. Okay, you have to modify this 512 to 5, whatever. This is the modification that you have to do. You are modifying the classifier head. Okay, so now let's do that. Now these are the things that we already know. So you got this. Now, the in features, which is there. Now is the in features of the 6, which is, if you remember, let me print it and show it again. The in features is this 6 in features. This is you are getting, and then the out feature is number of classes. Correct. Now I have fixed the number of classes to 5. Therefore, you are modifying this to 4096 cross 5. Okay, and then so that means that every other layer now will have the pre-trained weights of VGG. Only this layer is modified with a random matrix. Okay. Now there are cases in which they actually keep the whole feature extractor as it is. They will freeze, saying that the grade there is no need to train this, so they freeze the gradients. So and then only train this classifier. There are a couple of methods in which they do that. Okay, that is fine. So as of now, what has happened is only in this part. Now you have a matrix now which is 4096 cross 5, which is randomly initialized, not having any pre-trained values. Okay, that's what you have did. Model VGG dot classifier of 6. Model VGG classifier 6. You just modified it nn.linear in features, which is the in features of the 6 to number of classes. Okay, then you ported the device and then keep it in the training mode. You're passing this dummy data, where there are 4 examples, with each example having a size 3, 224, 224. Okay, now then what should be the output when you pass it? For all these 4, for each of them, you should get a 5 length vector. Okay, that's what you should get. If I run that, you can see here the output dimension is 4 cross 5. Okay, now this is how you modify the classification head. See, and again, now I'm repeating this again and again. The input is still 224 cross 224 cross 3. If you want to modify the input, let's say that you want to do it on MNIST, which is 28 cross 28. Now you start and recompute the values here. Okay, everything has to be recomputed so that the input here modifies. Okay, now this is for VGG 19. The similar thing is for the ResNet 18 and ResNet 34. You load the models, okay, and you define the in features. So ResNet 18 fully connected in features, that you change to number of classes, port it onto device. The same thing you do, you pass it, you get the value. This is how you take the classification head which is there and just modify the number of classes. Only that specific layer is having the randomly initialized weight. Everything else will have the pre-trained model. Okay, this is how we look into modifying of classification head, and then you can use it for any other training that you have. Okay, now then another important thing that are used, that our CNNs are used, is for feature extraction. Okay, or embedding extraction is what it is called. And one of the famous examples that we can think of is actually captioning. Okay, so you have an image, you have to caption it. So what do? You pass on the image and extract the before classification head. Now whatever is the output, you get it, and then take that and then pass it through a sequence to sequence model. Now because of which you can obtain a caption. Okay, now this is one of the interesting ideas that are used. So now let's see how do you do it. So now what do you need here is you have to go till the all the features, and then you don't need to go through the classifier. Okay, you don't need to go through the classifier head. Looking at here, now you have to pass your image till here, till this average pooling that is there, and then don't go into this classifier. Okay, that means that I just need till here, all the weights that are there till here. After this, I don't need this. Okay, that's what you will do. The same thing is for ResNet based models. Okay, that is what we are trying to do here. Okay, now first you get the weights. Similarly to the previous idea, I'm creating a new class VGG embedding, where in which I get the base models. I get all these ResNet weights. Now features, base model dot features. Now this will give me the whole feature extractor with all those layers, and then I get the average pooling. Okay, and whatever you get from the average pooling, you flatten it up, you get an embedding. Okay, now that will be of size 250, 88. correct, right? That will be the input for this row. Okay. Now you extract this embedding, correct? Now you pass two examples with 3, 224, 224. So you'll get two things with 250, 88. Okay. Now you get the features, you get the average pooling, you get your input, pass it through the feature extractor, pass it through the average pooling layer, and then flatten it up, and then return this X. You're not performing the classification, you're just extracting the embedding. The same thing is for ResNet also. Now, depending on whether it is ResNet 18 or ResNet 34, you load the model. You only have con 1, there's the first one, layer 1, layer 2, layer 3, layer 4, and then the average. So let's print the model and see. ResNet 18 model. If I print it, you see this first con 1, you want it. And then you want the layer 1, layer 2, layer 3, layer 4. You don't, even you want the average pooling, you don't want the FC, the fully connected layer, so that you can extract the embedding. Okay, that is what you are doing. First you get the first one, BN, ReLU, max pooling. This is your first operation. So just till here. Okay. Then you get this is layer 1, layer 2, layer 3, layer 4. Okay, see here, all of them are categorized as 4 layers. Okay, all the networks, layer 1, layer 2, and then pass it through the average pooling. So, and then FC is not there. Similarly, you pass it, you get 512. So exactly similar. Okay, this is how you get the embeddings. Okay, so now please remember, now all these are like Lego blocks. Okay, now you just need to find the proper size. If you match the proper size, now once you have matched the proper size, now you can actually work through them comfortably. Okay, now you just pass a dummy input and see whether the transformations, the matrix multiplications that are there are actually happening. Once it is done, it's perfect. We can go through it. Okay. Now, this is where we rest our case on CNNs. I hope you enjoyed the idea of CNNs, wherein which CNNs can be used as a classifier. CNNs can be used for the idea of transfer learning, wherein which you take the weights of the previously trained models and then you go ahead with that. And CNNs, which can be used as the feature extractors. Okay. So in the next two tutorials, we will be looking at RNNs, LSTMs, and GRUs. Okay. So we will be understanding them and implementing them. So in addition to that, we'll be coming up with a deep RNN, deep LSTM, and then deep GRU models. So preferably we'll be looking at them in the view of classification. And similarly, now we'll be looking at the sequence to sequence in a very generic structure which can be incorporated into any of these sequence models. So with this, we conclude the CNN tutorials. I hope you liked it and then you understood CNNs. So meet you in the next tutorials with RNNs. Thank you. Bye-bye.